Hello happy developers! In the last part of this tutorial, we are looking at some basic functions and function blocks that you will with 100% certainty get use of. In this part we will continue on the same track and look at more stuff that I'm 100% certain that you will use. We're going to look at the TwinCAT utilities library. The utilities library contains a number of useful functions and function blocks which with TwinCAT or the operating system can be called. It's one of these libraries that have functionality for everything between heaven and earth. Let's get started. Just as the various functions and function blocks that we went through in the last part resides in the TC2 standard library, the utilities that we will talk about reside in the TC2 utilities library. There are various types of functions in the TC2 utilities library. We have, for example, operating system functions, PLC functions, string functions, system functions, scope functions, converting functions, float functions, licensing functions, and a lot more. With the OS functions we can, for example, do shutdowns and reboots, get the local system time, and start processes in the OS. With the string functions we can convert all characters to upper or lowercase, find a substring in a string, and much more. Using the system functionality we can do things like stopping or restarting TwinCAT, setting it to config mode, or checking the CPU usage of a TwinCAT system. With the conversion functions we can, for instance, convert between different data types. The PLC functions, for example, provides functionality to write persistent variables, which we haven't covered yet, and doing measurements of execution. In the category Other, there are some goodies like a basic PID regulator, a memory ring buffer, and a real-time clock. And this list just continues on and on. As you can see, the utilities library is just a big box of tools that you can use in your daily workflow of developing PLC software. In this part of the tutorial, we will look a little bit closer on three function blocks. The first one is FB_memory ring buffer, which allows data records of varying lengths to be written into a ring buffer. The second one is the function block profiler, which can be used to measure the execution time of PLC code. The last one is the function block NT_start process, which can be used to start a Windows application from the PLC. We have actually already looked at a function from the utilities library when we looked at time conversion functions in part 5 of this tutorial. Back in this part of the tutorial, we used a function called fileTime_DT, where we converted a file time format defined as a struct into a date and time format. The TC2 utilities is one of the libraries that gets changed quite often. Maybe not every time there is a new release of TwinCAT 3, but still often enough that you notice it. There is just more and more stuff added to this library. I'll now demonstrate some of the capabilities of this library by showing some useful function blocks. We will start with the function block FB_memory ring buffer, which acts as a ring buffer for whatever data we want to store. It follows the principle of a FIFO, which stands for first in, first out. It means that the data records are read from it in the same sequence in which they were first written into the ring buffer. So the oldest entries are the first ones that are being read. If we fill the buffer with one entry past the capacity of the buffer, the oldest entry gets deleted. I will now demonstrate the concept of this function block. Assume we have an instance of the FB_memory ring buffer function block, and in this example we will just store integers in it. When you instantiate a ring buffer, you do so with a certain size. Let's assume that we have storage for 5 data entries. When we instantiate the function block, it will have a read and write pointer both pointing to the first location in the buffer. The write pointer points to where we'll write data if we add an entry, whilst the read pointer points to the location of where we will get the data next time we do a read. Now if we add a value, in this case the value 1, the value will be written into the first position of the buffer, and the write pointer will move to the next position. This means that the next value we insert will be stored in the second position. If we add another value, the right pointer will move once again to the next position. Now if we do a read, the oldest value in the buffer, in this case the value 1 that was in the first position, will be removed and the read pointer will point to the second oldest value in the buffer. Adding a new value moves the right pointer forward. And again, reading a value removes the value from the buffer and moves the read pointer forward. Now let's fill the buffer. In other words, let's write values into the buffer until there is no space left in our buffer. Now the buffer is full, and the right pointer points to the oldest entry in the buffer. We know it's the oldest entry as the read pointer is pointing to it. The read pointer will always point to the oldest entry in the buffer. Now let's see what happens if we add an additional entry into the buffer, even though it's full. What happens is that not only the right pointer will move to the next location, but the read pointer will too. The reason for this is that the ring buffer always has to point to the oldest entry for reading to fulfill the first in, first out requirement. This means that if we now again add one additional value to the buffer, then the write and read pointer will move simultaneously again. Adding another value, still same behavior. It's not until we do a read that only the read pointer will move to the next location and the write pointer stays. What happened here is that we read the oldest value, while the right pointer now points to the location where the oldest value was before. Reading one additional value empties the newly read value and moves the read pointer one additional step forward. Writing one value now fills the first empty slot with the value. We will now look at how we can use this function block. I thought that we would do a memory ring buffer for our event handling that we did previously. So we'll basically just create a function block that has where we can store our events. So the events are, in other words, these events that are declared with the type SD event. This was done in a previous part of this tutorial. Previously we just had an array of these events where we stored everything. And now we're going to use a memory ring buffer instead. For this, I put up the documentation for the memory ring buffer here. And the way you use this one is that you instantiate it, and then to add information or get information from it, you use something called actions. An action call is basically taking a bunch of code and giving it an alias. It's something I wouldn't recommend you to use if you develop new code. I think the reason Beckhoff has selected to use actions in this case is because this is probably something very old that's been taken already from TwinCAT 2, and where they probably used actions a lot, and then that just followed along. But there's actually no good reason whatsoever to use actions, just use methods instead. But here we have actions, so we have to use them because they're part of this particular function block. So we have different actions depending on what we want to do. So here, for example, if we want to write a new data set, we do it by calling this action. But let's just start with creating this function block or instantiating it. But before we do that, I thought we'd simply wrap our whole container to store events, our whole memory buffer, into one function block. So we have a function block that takes care of storing these events in this memory ring buffer. So I thought about we create a new function block and we call it event buffer, for example. And this guy will need to have an instance of the memory ring buffer. So we instantiate it. And again, this is a function block that resides in the TC2 utilities library. So we need to have a reference to that in our project. The next thing that this memory ring buffer requires is an actual buffer where to store it. So it needs a location to store this. This can be an arbitrary size. I mean, the bigger the buffer, the more data you can store in the buffer. So, but it still just needs a location, an array of bytes. So that's, we're gonna get back to this a lot, this array of bytes. So it's just a memory, a chunk of memory that we need to allocate where we can store these events. I've seen that Beckhoff provides an example here where they create a max buffer size and use that. And what they've done here is that they create an array buffer with the size like this. And we could start by doing this, so we can copy this and create, let's just give this a better name, buffer array, I think is better. And then they call this max buffer size is just a constant. So let's copy that, for constant. Oops. But the thing is here, I don't like this solution so much with just creating a buffer size with 1000 bytes, because that actually doesn't say us so much about how much we can store. I mean, yeah, it tells us that we can store 1000 bytes, or actually 1001, but it doesn't say how many events we can store, right? Because every event takes up a certain amount of size, right? So we can see here that here we have 255 bytes plus 1. We have a date and time, that's, I don't know, 4 bytes maybe. Every event, every instance of this structure will take a certain amount of bytes. But that's not interesting. What's interesting is how many events we can store. So what I would do instead is to simply declare a constant that we can call size of st event. And we can simply do like this, that we can call the operator size of, which will return the number of bytes of anything, a variable or a data type. And we can do size of st event. So we can do a size of the data type. And then we can call another variable where we simply declare how many events we want to be able to store. And we can call this max number of st events, which is of course much more interesting than max buffer size. And we call, say, we want to store, I don't know, 5. Let's just use a number that's not too big. And then what's interesting is now we have how many bytes every event takes and how many events we want to store maximum. Now we can create another variable or another constant that's called max or number of bytes for all st event, or yeah, something like that. Again, variable naming isn't my strongest side, but which is basically the other one times the size of every st event times the max number of ones. And then we can remove this guy and we can use this one instead. So now we actually have a little better feeling of how many events we can store here. It should be noted, however, that this doesn't actually guarantee that we will be able to store 5, because every time we store something in this buffer, there will probably be some overhead for padding. I'm assuming that this one will add some overhead on top of the actual event. So we might get 5, but I'm guessing we're probably going to get less than 5, but we'll see. So now we have a tiny wrapper here, which I kind of like this descriptive stuff, because then you can actually follow the code and understand a little bit of the thought, just rather than putting 1000 bytes, which doesn't say so much. Okay, the next thing I want to do is to add wrapper methods to wrap these actions. We want to be able to, we'll make a basic one, so we just make one where we can add data. So we create a method called add, or add event, maybe, add event. We don't have to return anything right now. We will actually return whether the addition was successful or not, but we can add that in a separate output variable. It public, and here we need as input we need to have the actual event, so we just call it st event that we need, and we're not going to use var input. We're going to use var in out, or var input. We can use reference to as well. Yeah, This is up to you. But I recommend you to use a reference instead of doing a variable copying, which will happen if you don't use a reference too. And now we need to use this action of the memory ring buffer. So we have the memory ring buffer function block, and we need to call this action that's shown up here. What this guy has as inputs and outputs are these variables. So it's pwrite, which is the address of the PLC variable of a buffer variable. So this is the data that we want to write. So in our case, it's the structure, the event structure. We have the cbwrite variable that says the number of bytes that we want to write. So that's actually the size of our structure. Then we have pread. This is something that we need to use when we read the buffer. So when we're going to read a structure. So this is where we should store the data when we have read a value from the buffer. So a pointer to a location that is a structure of the type st event in our case. This is the same as cbwrite, but for reading, so the number of bytes that we should read. So again, the size of the event. And then the pbuffer, that is an address to our buffer. So again, the address to our buffer, that's this buffer array. And cbbuffer is the, let's see here, max byte size. So that's the size of the buffer. We need to provide that. Okay, so for addtail, we'll simply need to provide the pwrite and cbwrite. So we start with pwrite. That is our event. So that's the address of st event. Then we need cbwrite, which was the number of bytes we provide. So that is size of the structure. And again, remember, because it's a reference to, it's basically an alias for a variable. So we can use all this address and size of just as a normal variable, which is very convenient. cbwrite. And then we don't need to provide read and cbread because this is when we actually get data. But we need to provide the buffer, so where we're going to store the data. And that's pbuffer, that's address of our buffer, which is buffer array. And let's see here, cbbuffer, that's the size of this buffer array. And we would also want to know whether this addition was successful or not. So we should add an output variable called error, for example, which is a boolean. Then we need to figure out how we get the error from this addition. And there is, okay, so the function block will always provide the latest, whether the latest action call was successful or not. So it returns true if a new dataset was added or removed successfully. So in our case, it's the addition. So we only need to provide the BOK from the function block. So we need to say, after calling this action, we need to check whether, we just need to say that error is mem ring buffer dot BOK. It's actually the inverse, because if it's okay, there's not an error. And if it's not an okay, then it's an error. So it's actually not. Okay, so that's add event. Then we need to do the other thing, that is to be able to get an event. And for this, we can use either one of these two. Get head reads the oldest data set in the ring buffer, but does not remove it. Okay, so we only read the data, but we don't remove it. A remove head reads the data, but also remove the oldest data set. So that's just as I shown in my, as I shown in the presentation, where you read the data and then it was just popped out from the buffer. And I think this is what we want to do. No, I don't like the naming here, to be honest. I remove head. That's not a good name because it says here reads and removes the data. So I think this should be called read and remove. Try to name your methods to what they actually do. That's gonna make not just your life easier, but anyone else that's gonna read your code. So if anyone at Beckhoff looks at this tutorial, then my suggestion to you is to rename this action, or even preferably even rewrite this memory ring buffer so it's using methods instead. But okay, so what we need to do is to add another method, and let's now call it read and remove, or just get and remove event, because that's what we're doing. And we don't have any inputs, but we have two outputs. We're gonna provide an SD event, and then we're gonna provide, let me think here. Yeah, we have to provide the event, the latest event that we're reading, but we also need to provide whether we got an error or not. And now we're gonna do exactly the same thing, but instead of writing, we're gonna do reading. So what I'm gonna do is to just copy this guy over here, and instead of add tail, I'm gonna call remove head, which isn't a remove head because it's read and remove head, but okay. And instead of write, we will read. Was it read? Yeah, p read and cv read. Read, and we're gonna read into the address of SD event. That's how we should think about it. And we're gonna do the number of bytes is for reading is the size of event. That's the amount of bytes we want to read from the buffer. And our buffer location is buffer array, and the size of the buffer is size of our buffer array, which in turn, the size of the buffer array is all this magic with our nice constants. So this code is a little cleaner. Now, finally, what we want to do is to make sure to return this guy, and that's the same as before. So we basically just return the last action call result from this buffer. So we just do b okay, b error is equal to that, not that one. Okay, so I think that's enough. I mean, we could and should probably also make a method that just returns the number of bytes available still in the buffer, or number of events still available, because maybe we want to provide it in an HMI, or we want to do it for error handling. I mean, there's possibilities to improve on this. I don't want to put too much time and effort on this. Yeah, because we actually look, if you look at the output, we can actually get the number of bytes, CB size, yeah, number of assigned data bytes in the buffer, but we're not going to care too much about that. What we want to do now instead is to simply use this guy. And what I'm going to do that is I'm going to go to my main program here, that's empty, and I'm going to do an instance of our function block. So now we have this function block that wraps all the handling of this memory ring buffer, so it's specific for our events. So we have effectively created a memory ring buffer for events. So let's instantiate this guy. And now we need some help variables, because what we want to do now is to test this event buffer. So we want to test by adding data into it and removing data from it, or reading and removing data from it. So what I'm going to do is to create a variable that's just a boolean that we can call add event and read and remove event. And for add event, we need to have an event that we're actually going to add. So I just create an empty event. So SD event to add. That's called SD event. And then for reading, I need an SD event to read. SD event. Actually, SD event to read isn't a good name, because that's a really bad name. SD last read event, because that's what it is, right? We want an event to add, and when we read an event, that's the last read event. So we're simply gonna do like this. If add event, so we're gonna change this online. We're gonna log into the PLC and change this online. Then we're gonna use our event buffer. So our event buffer now has these two convenient methods that we have created, which describe exactly what they do. Add event. And actually, you know what? I could even prove my point even further by renaming this add event to try add event, because we haven't actually successfully added the event if we get an error. I'm not going to do that, but actually if I did this for a project, for a customer or for anyone that I'm working with, I would actually rename this method and call it try add event or something. So it's obvious that when I call this, there's no guarantee this will work, because and what's so nice about that is that the developer or whoever is using this code or my code, if I put this into a library, then they will know, okay, try add event. That means I will have to have error handling in my code, and error handling is something very, very important. Yeah, but we'll leave it. And st event is simply our st event to add. And our b error, that's our, yeah, we haven't created a variable for that. So b event to add error. Boom. Right, that could happen, for example, if the buffer is full. Then we have to make sure that this add event is false again, so we only call it once. Otherwise, we're just gonna fill the buffer and just it's gonna explode. No, it's not gonna explode, but yeah, you get the point. Then we need to do exactly the same for read event. So we need to do if read and remove event, then we're gonna do event buffer dot get and remove event, and we're gonna store it in st last read event, and b error is gonna be stored in, yeah, we need a variable for that, b read and remove event error. So this will just return whether it was successful. So for example, it wouldn't be successful if there is nothing in the buffer. If we try to read from the buffer, but it's nothing's there, then it will not be successful. Okay, and then we need to set this to false so we don't constantly call this function block. But I think this is everything we need to run this code now, so we can test it. So we can test to add some events and read them. So let's compile. Log in. Okay, it's running. So let's try something. So first we need to have an st event to add, and we're gonna put some values here. So we can say it's a message and it's critical message. Event that is 42, of course, and event text is hi there. The date timestamp can be, what is it, 2021 10:30 22:51. Yeah, it's late evening, late Saturday evening. That didn't work. Okay, did I write something wrong? 10:31 dash 10:30. Yeah, 10:30. Okay, 080000. Yeah, I'm just gonna write this, and now we're gonna add the event. So if you change this guy to true, then the event will be added. And add event, event to add error is false, so it was presumably successful. And this we can easily check by simply now, here we have the st last read event, so we can check whether the addition was successful by reading from the buffer. So let's set read and remove event to true. And look, we get the data back. Okay, so it's working. Let's try to read again. Then it should not work because we don't have any data. Now the buffer is empty. Yeah, then we get nothing here, and we get an error. So let's try to add this event again. let's actually add 2 events and let's see whether we get the oldest one. Let's add this guy first. That's the wrong one. Add event. And then we change this, we add another event. That's something different. Let's change this to alarm. Let's just leave everything as it is, but change the event identity to 43, the message to hello world instead of hider. And then we add the event. Let me just think here. Yeah. Now we will read an event. So we should not get this one, but we should get the first one we added. That is the one that said 42 here and hider. So we read the event. Yeah, you see, so we get the oldest one, not the one that we added most recently. One final thing I want to do here is, of course, to add more events than we have in the buffer. So we already have 1 event in the buffer because we haven't read this guy yet. It's still stored in the buffer. So we should be able to add 4 more because we have 5 locations. But I think we're only going to be able to add 3 because, as I said, there is some overhead in the memory ring buffer of the function block, but we will see. We'll just add the same message over and over again. So we add this one. Now we have 2 in the buffer. Now we have 3 in the buffer. Now we have 4 in the buffer. Everything is fine. Let's try to add 1 more. Yeah, we get an error. So to actually have 5, you could simply just make this buffer slightly bigger. So we could just add another constant and call it overhead for memory buffer and just add a few bytes extra or whatever. But that pretty much sums up how to use this memory ring buffer.
The function block profiler is used to measure the execution time of PLC code. This is quite convenient, for example, when you want to understand what parts of your code takes the most time to execute, so that you can optimize your software. The function block takes the last 10 measurements and calculates the mean value and provides that into the output. The function block is fairly easy in its construction. There is 1 input for starting the measurement of the execution time and 1 input to reset the function block so that it's ready for a new measurement. The output busy is true until the measurement is completed, and once the function block is complete with the calculation, the output profiler struct provides all the measurement data. To use the function block, simply create an instance of it and optionally a variable to store the result. Then to execute it, start it with the rising edge of the start boolean and finish the measurement with the falling edge of the start boolean. Put the actual code that you want to do the time measurement of between these 2 lines of code. Let's play around a little bit with this function block now.
Okay, we're gonna test the function block profiler to measure execution. And for this I prepared a tiny function that calculates the factorial of a number. So the factorial, for example, is if we input 5 here, that's equal to 5 times 4 times 3 times 2 times 1. And then if we enter 0, the factorial of 0, then that's going to return 1. So that's what this function does, and that can be quite CPU intensive if the number is very, very high. So this is just a new project I've created, and we're simply gonna call this factorial with a number and see the execution. So what we need to do is to first, we of course need to make sure we have a reference to TC2 utilities. Next we need to instantiate the profiler, so we can just call it profiler and instantiate the function block profiler. And then we need a number to call with the factorial, and I'll just call it n factorial, and we can play around with this and set a different number just to see how the execution time will be affected when we change this number. The way we do the measurement is simply calling profiler with the start flag set to true, reset to false. Here we do our calculation, And then we simply call profiler with start equals to false. So everything between this line of code and this line of code will be measured. So here we want to call our function factorial. So we simply call the factorial with the number that we want to calculate, in this case n factorial. That we will change while we do our, that will change online during execution. So it's that simple. And then the output of this, there's a structure in this one as output where we actually have these numbers, but we can also store this in our O variable. So let's do that. Let's just call this profiler result, and that's called profiler. That's an instance of profiler struct. So this struct has some measurements like minimum execution time, maximum, and average, which is what we're interested in. So we simply do, after we finished with the measurement, we simply store the in a result, we store the output data, because the data is of type profiler struct. So we can look at this one while we're executing to see how long the execution time is. And that's basically all there is to it. So we compile. This function block is extremely useful because sometimes you just want to look what parts of the code takes the longest time. There's actually more modern tools to that. I'm not going to go through that in this particular tutorial, but this is a good starting point, at least for making the measurements. So now we're executing. We can see that, yeah, we basically have zeros here because the measurements are in microseconds. And the reason we get zeros is because simply this execution is very fast when we just use a factorial of 0. And so it's faster than 0 microseconds. And again, I'm running this off a virtual machine now on a quite fast CPU. So this is not a big surprise. And so what we can start to do is to simply increase the factorial from 0 to something bigger. So for example, 10. And we will write that. Still not a huge difference. The maximum execution time jumped up a little bit, but the average is still very, very low. I mean, extremely low because it's less than 0 microseconds. So we actually have to have a bigger factorial than 10. Maybe 100. Still nothing. So 1000. Yeah, now we can see that the last execution time is jumping around. So now we're actually starting to get into a number that we can actually measure using this function block, because again, the maximum resolution of this function block is 1 microsecond, which for a PC CPU isn't particularly much, or little, or yeah, you get the point. And then we increase it to 10,000, and now we can actually see the measurement jumping around a little bit. Again, this is running on a virtual machine, so we have quite a lot of jitter and the measurement isn't super precise. On a PLC, it probably wouldn't jump around as much. What's interesting here is that now we can actually look at the PLC task and the execution time, and here we see that we have around 30 microseconds execution. And let's increase this to 100,000 instead. Now we see we have, yeah, it takes quite some time now. Actually, it takes around 150, 200 microseconds to calculate the factorial with a number of 100,000. And if we look at the CPU, we can actually see there was a tiny jump there. And still far away from 10 milliseconds, which is what we run in this PLC cycle on. So, I mean, that kind of says a little bit of how powerful a PLC is using PC-based control, you know, because I'm just using one single core in a virtual environment in the PLC. I mean, we have plenty of resources to spare. So let's do, wait, is this 100,000? Yeah, that's 100,000. So let's increase it to 1,000,000. That's 6 zeros, right? 1, 2, 3, 4, 5, 6. And
yeah, then we actually get up to around 2 milliseconds, which is still far away from the cycle time of 10 milliseconds. And now we're actually calculating a factorial of 1 million, which is quite a big number. I mean, if we were to print the result of this one, I'm pretty sure that it wouldn't fit inside an unsigned long integer, the result. I mean, we can even do a Google. I think with Google we can just simply do like this. Yeah, it's extremely big. I mean, even the factorial of 100 is quite a big number. I mean, we can do 100 here. Yeah, it's a very big number. And I mean, if we have 1 million, then that's extremely big. That doesn't fit in an unsigned long integer, I think. So yeah, so again, it's just a few lines of code and you can do measurements. So it's very easy.
The last function block in the utilities library that we will go through today is the nt_startProcess function block. This can be used to start a Windows application from the PLC, which can be quite useful in many scenarios. At the first glance, this function block can look a little scary with all the inputs and outputs, but looks can be deceiving as this function block is actually very simple to use. Let's go through all the inputs and outputs. First, we can supply the net ID of the PLC that should execute the Windows program. This means default this will point to the local PLC of where TwinCAT 3 is running, but it can point to a net ID of another PLC. This means that we can execute a Windows application on another TwinCAT 3 PLC. The next variable is path string, which is the complete path to the application that we want to execute. Next we have the variable dirname, which is the working directory of the application that is being executed. This means that we can execute the application from another directory than where the application resides. Next we have command line, which gives us the possibility to add additional command line parameters to the application that we want to execute, if it supports any. The parameter start is used to execute the function block and start the process of starting the Windows application. The function block is executed with a rising edge of this parameter. The last parameter is the maximum timeout for the function block to execute its command. On the output side, we first have the busy flag, which indicates whether TwinCAT is busy trying to launch the application. The second and third output parameters give information of whether the execution was successful, and if not, an error identity which can be used to do fault isolation. To use the function block, simply declare it and provide the various input parameters. In this example, we have provided the net ID and timeout already in the declaration. It should be noted that the values supplied in this example are exactly the same as the default values, which means that they can be omitted as well. To start the Windows application from your PLC code, simply call it with the rising edge of the start input. In this example, we are starting the application notepad with the working directory of temp on the C drive and with the command line parameter of textfile.txt. This would result in our PLC opening the file textfile.txt in the folder temp if it existed using Notepad. If the file didn't exist, it would instead create a new file with the name textfile.txt in the temp folder using Notepad. Now it's time for some fun. Let's do a little bit of programming. Okay, so we're going to demonstrate the nt_startProcess function block, and to do this I'm going to have a slightly different approach. What I'm going to do is to use an open source project that I found that's done by a very nice chap called Ben. He has some interesting open source project on his GitHub. I highly recommend you to look into it. That's called tc3psping, and what this does is to execute a PowerShell script to call ping. So ping is a way to send a small packet, data packet to another host and see if you get a reply from that host. So you can ping Google or whatever site or whatever host and see whether you get a response. The problem with nt_startProcess is that you can't get any response back from a process. So you can call a process with parameters, but there's no way to actually get a response from it. There's no support in the function block to do that. But what Ben has done very smartly is that he has created a PowerShell script. So you have empty start process calling the PowerShell script, and then the PowerShell script through ADS, which we'll talk about in the future, writes into a variable on our PLC code back whether the ping was successful or not. So it's a two-stage rocket. You call the PowerShell script with empty start process, and then the PowerShell script writes back to the PLC code whether the ping was successful or not, which is really neat. So we can basically ping a host with this TwinCAT 3 project, which there's no native support to do that in TwinCAT, so there's no function block to ping or anything, but mixing this empty start process together with PowerShell, we can achieve this. And I was just thinking that we will go through this and we will do it together, looking at the code and see how this is done. And we can just see that we have a variable called ping reply in our code. So it can be either -1, then the ping is still pending, 0, then the ping was not successful, and with a return value of 1, the ping was successful. And this is just a screenshot that shows basically how the program will look like. But we'll look at it soon anyway, because we're going to download this project. And what Ben has done here is he simply shows the PowerShell script, and basically what it boils down to is that you can call the PowerShell script in this way, and this is what this actual TwinCAT project does through the empty start process function block. There are some requirements because the PowerShell script requires something called the TCXAE management, and this is necessary because the PowerShell script needs a way to write to our PLC code. So it needs this way to simply be able to update this ping reply on our PLC code. So there are some stuff we need to do here. So we'll just follow this tutorial. It says open PowerShell as administrator. We'll do that. And execute this on command. So just copy that. Yes to all. And then we go to the source folder. And for that, we actually need to download the project. So we need to clone it. And we're going to do this through a git clone. And I just want to point out right now, I'm just going to use git here. I won't talk too much about git. That's for a future part of this tutorial. That's more in the advanced part of this tutorial. So I'm simply going to do a git clone now. And then we have to go to this folder and execute as administrator. So I guess we do that with command. So we go to this folder. And then what did it say? It said source, main, modules, tc. And we run install.bat. So it does something. And we set NuGet to do on PowerShell. Yes. Stuff happening. Hopefully good stuff happening. Okay, something happening. Okay, and then it says the folder blah 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 should look like this. So let's check whether we have that folder. Yeah, there's stuff here and it looks about right. That means we have TCXAE management installed, which is a requirement for this PowerShell script to work. Now all we need to do is to open the TwinCAT project, which is this demo ping. Okay, the project is opened. Let's just adjust the real-time settings for our virtual machine. We run it on the isolated core, and let's look at the code. So what we can see is that we have our empty start process instance here, which is just called ping. We have the IP that we want to ping. Yeah, everything is documented by Ben, which is really nice. So this whole project is very well documented. And then there's all these parameters that are set up. And what we can see, there's some interesting things here. We can actually see that one of the parameters is main.ping reply, and that's actually this variable. So this is presumably used by the PowerShell script to know where to write the callback, so where to write the ping reply. And for the rest, the function block, which is the interesting part here, is just called with the PowerShell script. So this is presumably the whole PowerShell script in one line. So all of this constitutes the whole PowerShell script with the command line. So that, and in the command line, there's some more parameters added from this stuff that is actually necessary by the PowerShell script. So the only thing we need to do is to call to set the start boolean to true, because that's set as the trigger for this function block. Again, as I told you previously, the start input parameter is the trigger to actually launch this command. So I thought we'd just run this as it is right now with this IP address 127.0.0.1, which is the local host, that is this machine. So let's compile it. So we have a ping reply of -1, which is pending. We'll set the ping reply, the start to true. We call it, then we wait. And we get a 1. So yeah, that works. That's really neat. Now let's try to ping something else. So something maybe that Google's DNS, that's 8.8.8.8. I'll just manually try to ping it, because I think that's, yeah, that's somewhere out in the world. That's quite a neat IP address, by the way. Right, and -1, so we haven't received a response. We'll just set this to true. And 1. Yeah, that's really neat. Let's try to ping something that doesn't exist. So I don't know if we can ping 0.0. Yeah, that's a general failure. We like general failures. Then we get a 0, so it was a failed ping. So I must say this is a really neat way to use this empty start process, because we can basically achieve stuff that's not existing in any TwinCAT library. So by utilizing this empty start process, we can actually use something that's running in Windows, so in the user space applications, so in non-real-time applications, and combine that with TwinCAT to get a really useful function. So I think what I want to finish with saying that I'm really happy to see these open source projects pop up more and more, because there's some really neat stuff here, and I personally learn a lot by looking at these examples, and what Ben has done here and many other people is truly amazing. And I really appreciate that the open source scene for TwinCAT and PLCs in general have started to get bigger. So that's really good. As you see, there is just a lot of stuff in this library. Going through all of the functionality in the library would probably require a multi-part tutorial in itself. But what I highly encourage you to do is to go to the documentation for the library and just look around. Some of the functions and function blocks are going to get stuck in your head, and next time you encounter a problem, you're going to think, aha, there is a function block in the utilities library I can use to solve that problem. Looking around the utilities library, you'll most likely find a few ones that look interesting and that I haven't covered here. create a simple program and try them out. Play around a little bit. There is nothing that's more fun than discovering and learning. In this tutorial, we have so far only been talking about software. In the next part, we're finally going to look at some hardware, which I think is going to be fun. Thank you for sticking around. I'll see you in the next part.